Alright, let's get this shit going. Today, we're researching Fred. So we need to get some kind of knowledge for how it works. And to be transparent, I'm not sure I understand a thing about it. So here is my TLDR. So Intel Fred, I need to start writing things like I said I would do like a year ago. So Intel Fred. So what is Intel Fred? So Intel Fred, from my like 1 hour of research, is a couple of things. So there is a problem with x86 where whenever you want to switch from well, user mode to kernel mode, or we commonly call ring 0 to ring 3, or the other way around. So whenever you want to go from ring 0 to ring 3, so kernel mode to user mode, you need to call specific commands. So those commands are either, if you want to go from 0 to 3, they're returns. And if you want to go to user mode to kernel mode, or R3 to R0, that looks like an O. Holy, okay. All right. If you want to go to that direction, then it would be, well, there's a couple of choices. So it can be a syscall. So if we just, let's make this another color. You know what? Yeah. So if we do this, I need to write currently. So, shit. So the blue is from secure to unsecure, so those would be return. While if we look for the green, it would be, sorry, I'm trying to focus, okay? It would be, so calling a syscall, there would be, there could also be passing by in the well, an interrupt. And there's some others that I don't know. Let's put it in the right color. Okay. So those, so when you want to switch from user mode to kernel mode, there's these ways. When you want to switch from kernel mode to user mode, there's this way. So the question is, how do we make the process of switching simpler? Because right now, the issue that I believe they have is that we have a lot of convoluted pathways that are created just to grant kernel mode or to remove kernel mode. So essentially, we're going to do a bunch of call to the IDT. Is that how it's said? IDT. And that would stand for interrupt descriptor table, which, if I remember correctly, is essentially a list of address for specific interrupts. Okay. So, you make a bunch of call to this. And whenever you make a call to this, from my understanding, it becomes spaghetti. Okay, so you will like make a call to this, and then down the line, it might ask you to do yet another call to this. Let's put it in orange. And then it might ask you to do another, and then another, just under one call. So you would end up like doing this thing again, and again. So the solution to this spaghetti is Fred. Now what Fred adds is a specific mode that whenever you set your CPU to, it will only switch from one from kernel mode to user mode, or from one ring to another ring, using Fred related commands, or using the Fred framework. And from my understanding again, it's using a modified stack. So when I'm talking about the stack here, talking precisely about... Can I have a real shape? Talking precisely... Bro, can we really not? Oh, there's arrows. I like it, but... Okay. So I'm talking about the... like a stack in memory, right? So whenever you have a stack, you have a part that is the actual data within the stack, and you have another part which is... Let's put it in blue, which is essentially kernel maintain information. So the kernel will hold... Shit. Who knows what I'm doing, okay? So the kernel will hold some information here just to manage the stack, to know what the fuck it does, and to do cool things with it. I say the kernel, but it's probably mostly enforced by the CPU, but who cares? So that thing here now has additional things within it. So it's a little bit longer, and the additional things that it has is essentially the ring level of the stack. So that place within the stack shouldn't be editable by the user space, so we can just shove things into it, and here they will shove, like, this is a stack that is based on, let's say, a ring 0, or a ring... I need to write these down. Ring 0 to 5. Let's do like they do on the kernel. Meow. Hi, Rust. I'm gonna finish my yap, and after that, I'll yap about other things, I guess. So, yeah. So, here, there is a place in the stack that will essentially tell what the ring is for the stack. So, like again, I have no fucking clue how this works. I'm going to read more about it. But my understanding is that by having this ring, it's easier for them to, like, have multiple stack together and not have to check for kernel mode every fucking time. So it reduces the amount of checks. But hey, it feels retarded, so I have no idea. So yeah, let's try to understand this, because I found out that nobody fucking explains this. At least nobody does correctly. You know, whenever Fred is not explained anywhere correctly, that it means that we have no fucking idea what it does. Or maybe we can take a look at the merge thing. Have you seen PC 2.0? Is it a meme? What? Is this it? Or did I just fail on something that had no relation? That's what I thought. You're gonna have to send a link. But yeah, reading this doesn't make it any clearer. Asking the AI did, though. Oh, man. So let's just... You know what? I should have started with the kernel. Maybe let's read that 4onyx article. Or maybe, who knows? Did I note things down back then? I think... Wasn't 6.9 like my first one on this channel? It was garbage. If it was. Yeah, probably note down nothing. Alright. Alright, after 2 years of talking about Fred as flexible return and event delivery for overhauling how transitions are done between privilege level CPU rings, the support code was finally in good shape for merging, now with the Linux 6.9 kernel. Linux Fred is designed to allow for lower latency transition between privilege levels and more robust software use. As part of Intel Fred is also the LKGS instruction that was separately already plumbed into the Linux kernel and open source compilers. Intel Fred replaces IDT event delivery and a big step forward with future Intel processors supporting Fred. Okay. We were expecting to see this code for Linux 6.9. Okay. Let's go look at the merge window. The merge. Not the merge window, just merge. Fred is a replacement for IDT event delivery on x86 and addresses most of the technical nightmare which IDT exposes. Exception cause register like CR2 need to be manually preserved in a nested exception scenarios. God damn. Sorry. Alright. Exception cause registers like CR2 need to be manually preserved in Nex. Okay. Oh, because now it would be within the... Holy shit, that's so bright. Okay. Okay, we're starting to get it. We're starting to get it. Okay, hardware interrupt stack switching is suboptimal for nested exception. As the interrupt stack mechanism rewinds the stack on each entry, which require massive effort in the low-level entry of code to handle this. Okay, I have no clue what this means. IMB, you're in hell? I'm doing a bit better on my side. I hope that you're doing okay. Oh, Tom Gleeksner! You know what? Maybe I should just check. Again, doing a sanity check. Okay. They enable it by default. Okay, it's big enough that I can think of speaking about it. Okay. So TLDR MB, well, not TLDR, but like quick introduction. We're going to cover Fred. That's going to be the big thing that we'll cover. So I'm trying to understand how it works, and for that I need to understand how, like, registers and interrupts and exceptions were handled. Which is a big feat, but it should be fun to show. We have 2 weeks. So, yeah. That's the meme, that's the meme. Okay. We'll try to understand what the fuck that means soon. No hardware distinction between entry from kernel or from user, which makes establishing kernel context more complex than it needs to be, especially for unconditionally nestable exception. What the fuck is an NMI? Oh, thank you. Non-maskable interrupt is an hardware interrupt that cannot be ignored or disabled by the CPU. It is typically used to handle critical hardware error or system diagnostic, especially in scenarios like system hang and or crashes. Okay, cool. Hi, Fred. Shiro! Alright. So I guess we'll probably need to explain those, because they're going to be core to what the fuck the issue is. But for now, we're just trying to get a vibe for it. If you want to, I can do a TLDR for you. I have literally some drawings. NMI nesting caused by RRET. So I would be interrupt return, okay? Unconditionally enabling NMIs. Fuck, I have no idea. Which is a problem when the perf NMI takes a fault while connecting a stack trace. That seems specific. Okay, partial restore of ESP when restoring to a 16-bit segment. What does ESP mean? That's definitely not it. Alright, I'm not going to find it. Cool. Limitation of the vector space, which can cause vector exhaustion on large system. When they say vector space, they're related to the IDT, right? To the interrupt description table. No, not table or something. I'll watch the video when released. My brain is not working these days, so I should not be able to integrate new knowledge. That's fair. I'll still TLDR you in, okay? I just wanted to do it. So, when we switch from kernel mode to user mode, or the other way around, okay? We use things like return, syscalls, interrupts. Now, the issue seems to be that IDT, which is the interrupt descriptor table, is used for most of these things, which is garbage, because it means that we have spaghetti code where an interrupt calls another interrupt that calls another interrupt, and that like loses a bunch of data in between. So we have to do a bunch of shit that is slow as fuck. And Fred seeks to relieve that by adding some data onto the stack that this CPU can actually trust in order to tell the version and a bunch of shit. Not the version, but the ring level. That's the TLDR for, like, my knowledge right now. I don't know anything else. inability to differentiate NMI sources. Okay, Fred addresses the shortcoming by an extended exception stack frame, which the CPU uses to save exception cause registers. This ensures that the meta information for each exception is preserved on stack and avoids the extra complexity of preserving it in software. What the fuck, Fred? Hardware interrupt stack switching is non-rewinding if a nested exception uses the currently interrupt stack. I have no fucking idea what that means. Holy! Fred guarantees full restore of ESP. Haha! What is ESP? Wouldn't ESP be like the totality of registers? Or something like that? So if I do... Extended stack pointer is a 32-bit register always point to the top of the stack of memory. Okay. I don't think that's what... Because my... True. Stack pointer, yeah, but... Yeah, so they wouldn't... Like, they're talking about something else. Okay. Well, maybe not. Who knows? Fred does not put limitation on vector space by design because it uses a central entry point for kernel and user space, and the CPU stores the entry type exception trap interrupt syscall on the entry stack along with the vector number. The entry code has to demultiplex this information, but this removes the vector space restriction. The first hardware implementation will have the current restricted vector space because of lifting this limitation requires further change to the local APIC. Okay. Fred pays with stack, so restoring stack pointer makes sense. Yes. Okay. My question here is, how the fuck could it not be 4? That's like the part that doesn't make sense to me. So like there must be more than this. Or could it be 4 and it's just something that like is assumed that it could be an issue? I don't know. Fred stores the vector number and the meta information on stack, which allows having more than one NMI vector in future hardware when the required local APIC change are in place. Multi-call might overwrite entries. I don't know. Oh, maybe because of the vector space thingy? There could be a... I don't fucking know. Can you watch Passion? Oh, yeah. Here you go. Fred stores vector number and... Okay. Oh. Yeah, okay. So expanding this the stack frame to accommodate for extra 16-byte Fred requiring to store the context and meta information. So that's here. Did I really close it like a Buffoon. No way I did. Bro. I did. Where's my x86 P-trace? Alright. So if we look... Like that's the extended things for Fred. So you have like that struct thingy. And you have that struct thingy. Funks. Right, where was I? I think it would be good for me to read how the IDT works in the first place. Are they okay? What do you mean? Confused. You were making a joke, probably? Fast return and event delivery. Yeah. What's the issue? Oh, maybe it changed name through time. Like it's flexible here, but maybe back in time it was fast. I don't know. Probably just a typo. Because it is also fast, okay? That's the point. Yes, it should be Intel only. Because there's actual change, like you need a specific silicon for it to work. Hello, Stan. As long as it's not your deathbed, I'm okay with it. Hello, bed. Fred, bed. Fed, okay? That's... we just need Ned, okay? Alright. What a unit, by the way. Gleeksner. Alright, let me just relearn what IDT is. Interrupt descriptor table. The interrupt descriptor table is a data structure used by the x86 architecture to implement an interrupt vector table. The IDT is used by the processor to determine the memory address of the handlers to be executed on interrupt and exceptions. Okay. The detail of in the description applies... The details in the description below apply specifically to the x86 architecture. Other architectures have similar data structure, but may behave differently. The IDT consists of 256 interrupt vectors, and the use of the IDT is triggered by 3 types of event: processor exception, hardware interrupt, and software interrupt, which together are referred to as interrupts. Cool. And if I go into this, they probably all have specific code, and the CPU will just know where to throw it depending on what the fuck it is. Is that the meme? I don't know. Oh, it's explained. Alright, we're almost there. My friend had a problem with QEMU today. Turns out it was a new kernel regression. Well, they're making a lot of change. They're making a lot of change. Processor exceptions generated by the CPU have a fixed mapping to the first up to what? Oh, okay, it's just shitty wording. Processor exception generated by the CPU have fixed mapping of up to 32 interrupt vectors, while 32 vectors are officially reserved, and many of them are used in newer processor. The original 8086 used only the first 5 interrupt vectors, and the IBM PC IDT layout did not respect the reserve range. I wonder if new NVIDIA hardware will work with Linux. Why wouldn't it? It would be crazy retarded not to. AMD and Intel have joined the x86 ecosystem advisory group to standardize Fred. AMD is expected to implement Fred for its Zen 6 processor, replacing the legacy IDT system. Woo! That would be good. No way. Do you have a source for that? By that I mean something that's not just AI. At launch, Windows only has partnership with Microsoft. Don't know if I get it, but it's all good. Oh, here. Okay, that's kind of cool. Should probably note that down. Fred initially Intel only is expected to be added to be part of Zen 6. It is one of the victory, one of the gain, one of the benefit brought by I guess this. Yay, gaming. Oh, 2 L's, okay. Cool. I have way too many tabs. Somebody kill me. Alright. Can we just get some knowledge? You know what? I need to start my Zizek vibe right now. Get us slug the fuck in and talk about communism. Okay. Hardware interrupt. Vector number correspond to the hardware RIQ numbers. The exact mapping depends on how the programmable interrupt controller, such as Intel E154, okay, is programmed. Okay. So the motherboard. While Intel document IRQ 0, the motherboard for old system, probably integrated now. While Intel document IRQs 0-7 need to be mapped to vector 0x20 to 0x27. Okay, they're mainly talking about old ass shit here. To the kill me comment. Okay. Shit. I'm so confused. Alright. YouTube made my comment. That's all good. That's all good. Okay, software interrupt. Vector number are defined by the specific runtime environment, such as IBM PC BIOS, DOS, or other operating system. They are triggered by software using an int instruction, either by application, device driver, or other interrupt handlers. For example, IBM PC BIOS provides video services. Okay. And Linux provide the syscall interface at the vector 0x80. Okay. Am I to believe that you can just modify these? Oh no, you would need to be kernel mode for that, so you're never going to be able to do that while being a user. Okay. Okay, this makes sense. Cool. What do we mean by real mode? Real mode, also real address mode, is an operating mode of all x86 compatible CPUs. The mode gets a name from the fact that addresses in real mode always correspond to real location in memory. Okay, so it's probably not the mode that we're running on. Wait, do we run in real mode? Does Linux run x86 CPUs in real mode? Protected mode. Isn't protected mode limited in memory? Am I retarded? Fuck. Real mode is a simplistic 16-bit, okay, I'm retarded, 16-bit mode that presents on all x86 processor. Real mode was the first mode designed and was used by many early operating systems before the birth of protected mode. Okay, cool. Protected mode is the main operating mode of modern Intel processor and clones since the 80-86 on 8386 and later the 32-bit protected mode allows working with several virtual address space, each of which has a maximum of 4 GB of addressable memory, and enables the system to enforce strict memory and hardware I/O protection, as well as restricting available instruction via rings. Instruction set via rings. Okay, cool. A CPU message retracted. A CPU that is initialized by the BIOS starts in real mode. Enabling protected mode unleashes the real power of your CPU. However, it will prevent you from using most of the BIOS interrupt, since these works in real mode. Who the fuck is spamming my ass? I'm streaming, bitch. Money's calling. Because my net worth is taking a dump today. As it's still, we're taking a 1 second pause, okay? 1 second pause to see fucking red. Okay. 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 We're good. Okay. Cool. So, now back to this. So, we're running in protected mode. Cool. Got it, Chief. All right. So interrupt descriptor table allows us to put down a bunch of address for how to handle specific things. There's some that we can set ourselves to be whatever the fuck we want. There's some that are provided by the hardware. Okay. I'll fuck something up and people will yell at me anyway, but I think that we got that part. What about long mode? Oh, fuck me, bro. I saw it and I was like, nobody's going to ask a question, nobody's listening. Protected in long mode, IDT, let's just Google it first. Bro, my middle wheel needs to work. Only people doing nothing gets nothing wrong. True! Thank you for making me feel good, okay? Love you. In the x86-64 computer architecture, long mode is the mode where 64-bit operating system can access 64-bit instruction and registers. 64-bit programs are run in a sub-mode called 64-bit mode, while 32-bit program and 16-bit protected mode programs are executed in sub-mode called compatibility mode. Oh man. Oh, that's what I searched earlier. Bro. IA32E. Ah. Okay, let's reread that and actually understand. What is IA32E mode? Several operating mode of x86-64 processor. Real mode, protected mode, virtual 8086 mode, and IA-32E. Explain a few professional vocabulary. What the fuck? Vocabulary. I don't know. IA-32 x86 processor architecture supports 3 operating modes and 1 kind of operation mode. What? Okay. Wait, I'm retarded, right? Okay, I'm retarded. IA-32E. In IA-32E, the processor supports 2 sub-mode, compatibility mode, and 64-bit mode. The 64-bit mode provides a 64-bit linear addressing mode and supports a physical address space exceeding 64 gigabytes. Compatibility mode allows most traditional protected mode program to run without modification. Okay, so that would be long mode. Okay, long mode and IA-32E. Same things? No? Okay, long mode. Oh, fuck, I get it. Okay. So you put the CPU... What about Unreal mode? Whoa! So IA-32E is the mode that you set your CPU to, and then whatever the fuck you're running will like fuck with this, I guess. Real mode versus fake mode. You're not real. I'll send that CPU to conversion therapy. Alright. Fuck the DRL, okay, fuck the DRL. Long mode, 64-bit mode, compatibility mode, okay. Long mode. Kernel 64-bit mode users must be 64 bit. Ha! There's a lot of 64-bit there. Compatible mode user, 64-bit or 32-bit. Forcibly flat segment. Okay. Does not support task switching. Okay. That table is missing Unreal mode. It's because it doesn't exist. Okay? There's no Unreal mode. Don't fuck with me. Don't fuck with me. I'll search for it if you... Don't stop. Stop! Alright. Okay, can we know... Wait, there was a more complete thing I was looking at before. Can we know what the fucking registers are? And yes, it needs to be a F-word register. Okay. I read all this and I had no clue what it was talking about. Oh man, in x86 computing, Unreal mode, also big real, big real mode. You know what? That sounds like something from like from an old AMD like bulldozer bullshit. We're coming with a new type of CPU. CPU that can cook an egg. A CPU that can burn a hole through your chest. A CPU that is overclockable to 6 gigahertz without having to be cold. It will melt your heart. Unreal mode also comes as big real mode. Like, what the fuck are we talking about? Flat real mode, is that like a dig? Is big real mode having big tits? What the fuck is this? Voodoo mode. Does it come with your own like you know what, I'll just put this. Does it come with your... I'm trying to not say the N-word right now. Does it come with your own shaman? Okay, with your own... I was about to say Dieu donné, but it doesn't work because you cannot be... You cannot have God in your name if you're going to be a voodoo guy. Maurice. Does it come with Maurice? No? No, Maple, we don't buy slaves anymore. Okay, cool. We're going close to the sun right now. Holy shit. That's going to be cut out of the edit. Maybe not. Okay. Okay. In which one or more segment descriptor has been loaded with non-standard values. Okay. That sounds like in which we decided to fuck with you. just for the lols. For the love of the game. Like 32-bit limits, allowing access to the entire memory. Okay. Contrary to its name, it is not a separate addressing mode that the x86 processor can operate in. It is used in the 80. Okay. What is a segment descriptor? In memory addressing for computer architecture, segment descriptors are part of the segmentation unit, used to segregate... No, okay. Used for translating a logical address to a linear address or to the address of a page table. Okay. So this is a PTE before PTE. Okay. Oh yes, an STE, or one letter from an STD. That sounds like IBM. That's the closest to sex they'll ever get. Okay, we're deep in the jokes right now. We're deep in the jokes. And we're deep researching things that are so far from our goal. Holy shit. We get it. There's modes. Clip it. Clip it. Where the fuck were we? We're gonna have to reread this. Look at all those acronyms. What the fuck? Oh, I think I'm good for... I think I'm cooked for today. Can we find a good thing that describes all the registers? Like, can I have an x86 64 list of registers? Oh! The fuck am I supposed to do with this? Okay. Oh. Okay, I think I get it now. Okay, then it's... Yeah, that's not bad. RAX. Okay. Segment register. Code segment. Data segment. Stack segment. Ooh, that one is a little spicy. Extra segment. General purpose segment. General purpose segment. Segments CS, DS, ES, and SS are treated as if their base was 0, no matter what the segment descriptor in GDT says. Exception for FS and GS, which have MSR to change their base. Look at APX or more register. Are you fucking kidding me? Do we have it here? Probably not, eh? Why do I copy these things? I don't know. I covered this. You're recycling my shit. Ah! No! I'm getting recycled. Do they have it here? I'm getting recycled. Okay, this is too dumb. No, but that's pretty good. I think we're gonna be able to do that kind of thing. Like, oh, I don't understand a thing. And then we're gonna look at it, and we're gonna say, oh fuck, doesn't give me anything else. Ha ha ha. Cool. What do we have here? Nothing. Kill yourself. Okay. Oh, the CRs. I want the CRs. I like this one, okay? IA32 Epper. Oh, what? Extended feature enable register is a specific model register added in the AMD K6 just before they made it a cassette. Haha. Okay. To allow enabling the syscall sysret instruction and later for entering an existing long mode. Okay, cool, but I don't give a fuck. CR. Let's look at all the CRs. Ooh, those are cute little values. Could I talk about CR7 or something? Wasn't there a CR7 or... No? Okay. Get me in. Can we highlight them all, or I'll just fuck off, I guess. CR4. CR4. Well, fuck it. Let's look. Let's look at CR4. What the fuck you want me to say? Search for space CR. That was a bold fucking choice to click on image, okay? I just thought about it. That was a bold choice. Streaming and clicking on... I don't know what... Are you meaning in there? Oh, man. I'm way too retarded for this. Oh, no. Oh. Oh. CR2 and DR6. CR2 control register contain a linear control address which trigger a page fault. Okay. And we said DR6. It permits the debugger to determine which debug condition have occurred. When an enable debug exception is triggered, low order bit 0-0 to 3 are set before entering the debug exception handler. Okay! Not bad, not bad. Look at all those things. Alright, I'm done for today. I'll go. And we'll see each other tomorrow, okay? Love you all. We'll need to do more research. I'll probably read a bit more than today. But yeah, that's our target today. Well, not today, but for this kernel, it's going to be knowing Fred in and out, understanding why, where, when, and how much I'll kill myself. CR7, that's a 3D printer, okay? Oh, it is, but... No! No! I'm getting fucked! Okay. 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 I need to sleep. Guys, I love you. Bye-bye. Okay? Bye-bye.